Okay, so I've found some interesting YouTube videos lately on genetic algorithms, and I decided I'd try and learn about them, try and write my own programs to use them, get familiar with them, and be able to use them in other stuff. I had hopes of using it in Flow 3, but like the other projects I've been doing, but I'm not too sure if I can do that. Either way, I've had fun learning them and figured I would show you some videos of what I've been doing. So first of all, what I tried to do was a very simple genetic algorithm. I tried to generate a phrase or a string, sorry, a string of characters. So you can see here, this is what it would do. This isn't the actual genetic algorithm. This is just a brute force method to illustrate how slow brute force is. But you can see I'm trying to find cat, and what I'm going to do is I'm going to generate so population size, how many times I'm going to generate that string, random string. So I'm going to generate 1 million random strings. The target length, so it's just the length of the target, there's three characters in cat. Now the population, so basically this doesn't have to be done this way, this isn't the best way to brute force it, but it was done this way because I just borrowed the code from the actual genetic algorithm. But basically all it's going to do is going to generate 1 million strings completely randomly. This is this part up here. There's 95 different characters to choose from the ASCII table. I'm going to flash that up on your screen now so you can just see what I've actually picked this from. So you can see there, got all the punctuation, I've got upper and lower case. So pretty much anything you type into target it will eventually find, given enough time, but you'll see soon that time is a ridiculous amount. You can also see my RAM usage up there on the screen. It's over, you see my mouse up here? Yeah, there you go. So you can see my RAM usage because you'll see that this actually kills your RAM doing it this way, because I'm storing it on the list. Obviously you wouldn't have to do this if you're doing a more efficient brute force method, but even so it's still going to be terrible is my point. So yeah, 95 to the power 3 for 3 letters. Takes roughly 1 million to find one version of cat. So we'll run this, we'll see how long it takes to do 1 million, see if it finds one. And then I'll add one more letter to it and let it run in the background. So it didn't find cat. Try once more, it should find it. There we go, so it found one. Now if we had one more letter, that's obviously another power of 95, so we're going to need to do like 2 zeros on the end of this to have a good chance of finding one. Now I'm going to save this, I'm going to run it, and I'm going to leave that RAM usage on the screen. You can see that gradually climb, you can see it already slowly growing. It will grow, it'll probably hit about 15 gigs, something like that. I'll just leave that in the background for now. You can see how terrible this is. This is going to take a long time to run, and we'll go over the genetic part right now while this runs. So I might end up cancelling that, I'm not sure exactly how long it'll take, but you'll see it's going to take ages. Okay, so the genetic algorithm part, for those of you that don't know what a genetic algorithm is, there's basically 3 steps to it. You have an initial population, so in my code this is it right here. It's the exact same code as what I've just showed you right here. It's just the initial population is just randomly generated to be the same length as the target, so in this case 4 letters. But this length can change. You can see it doesn't actually take in any hard-coded values, it takes in the value of the length of this. So that's the initial population. Now step 2 is you need some way of creating you need some way of scoring the population, so how good they are, how good each element is, how close it is to your target, how right is it, sort of. So I'll show you what mine is for this. That's down here. So what I chose to do was I'd check each letter against the target, and I'd say if the letter was right, your fitness score goes up by 1. If it's wrong, you check the next letter. So basically it's just, if you've got 4 letters and 2 of them are right, it's going to get a fitness score 2. Really simple, and returns the fitness. So now fitness is going to be a list of fitness scores for each target. I'll probably print this out in a minute. We'll see like what each step does. Yeah, we'll get to that. So we've scored the population, Now what we need to do is generate the next population. So first of all, we should probably check, do we have a right answer? If we do, great, we're done. If not, then we need to generate the next population. So the next population is generated by, in this case, not for all genetic algorithms, but in this case, we do some crossover. So what we do is we take in the population, we take the target, and we take the normalized fitness. Now the normalized fitness, this is taking in the fitness, and it's just going to sum up all the values and then take every fitness score and make them all add up to 1 eventually, basically. So it just returns sort of a list of like really small numbers that will total to 1. I'll print this out again in a little bit and you can see, but the reason I do this is to make selecting my next population a bit easier, because I'm picking it based on probabilities. So if, say, we've got 4 characters and 2 of them are right on 1 and then the rest all have no characters right, it's probably not worth picking a parent that has no characters right, since you're better off just randomly selecting characters. Taking traits from a parent that has a fitness score of 0 will not help you at all. It will just mean that your next generation is worse. So you always want to take from the best parents, or more likely to take from the best parents. So all this helps me do is just convert each fitness into a probability of being chose. Now this is why I use it in crossover instead of the actual fitness, because the actual fitness doesn't range from 0 to 1 like a probability does. So yeah, that's why I converted it first. Now to create the new population, what I do is I create a seed. This is just a random number, 0 to 1. Then I loop over the normalized fitness, and for each normalized fitness I take this away from the seed. Now this total of normalized fitness is 1. The max seed can be is 1. So eventually this is going to hit 0. When it hits 0, we're going to say, right, that's the parent. That's parent number 1. Now it's more likely to hit 0 on a parent that had a high normalized fitness, so a high probability of being chose. Hence why this system works. I'm not going to go too in depth on this. Hopefully you understand why it works. Now this bit of code here is just copy pasted, up to here. So this bit of code right here is copy pasted below, except it picks parent 2. So we've got DNA1, DNA2, these are the 2 parents. And now to select the child's DNA, what we do is we pick a random number again, and we say if this number is above 0.5, we're going to take from parent 1. If it's below 0.5, we're going to take from parent 2, and that's our new child, our new DNA. Then append this to the new population, repeat for the next child we need, go on, and then return the new population. So hopefully you get this bit. If not, I'll run it in a minute. Hopefully you'll see. So that's the next step of genetic algorithms. You score your population, you've then got to generate the next one, then you repeat. Now when you do that, you might notice, say if we start with a population of 10, you might notice patterns. You might notice that, say, you're getting the same letters over and over even though they're wrong, because it's got no other letters to choose from. So if we've got 95 characters to choose from, but we've only got a population size of 10, we're going to be missing a lot of letters. There's going to be a lot of letters that can't be found in our population, that can't be selected for crossover. So we need some form of random element to it that's going to add in these extra characters that we need. So that's where mutation comes in. That's what this mutation rate's for, and that's what this function's for down here, mutate. So what it does, it takes in the population. This population is after crossover, so they've got the child DNA, and now they enter mutate. Once they enter mutate, they basically have a random chance, whatever this mutation rate is that chance, of randomly having a character swapped to a random letter. So again, I'll print this out in a sec, but hopefully you get that. This is probably the simplest part. It just picks a random character, swaps it for a random character, and that's the mutation. It doesn't always do that, it just does it sometimes, just to add a little bit of variation in. You can see this does it once in 1,000. One in every 1,000 characters will be swapped. So not very big, but enough to add variation to the population in case you don't initially hit your target. So I'm going to up this population size to 100, and I'm going to print a couple of stuff out. So I should have mentioned, actually, this is all in a while true loop. So basically you just loop infinitely over this process, and when you find your answer you break out. So here's where we find our answer. If we've found an answer that's correct, we print success, we break, and then we return our generation count, because there's an extra little loop at the bottom here that just is going to call this function 10 times just to get a nice little average over a couple of iterations, to stop like random variation stuff. So you can see roughly sort of the time it takes. This thing down here is just basically calling the function. It's not important to the genetic algorithm at all. So yeah, we call population, initial population. Now that's only ever called once. You'll see this is out of the loop, because we only initialize the population once. After that, the population comes in the previous population. So we score it, check if we've got our right answer, we normalize the fitness, we cross over the fitness, we mutate. Sorry, we don't cross over, we cross over the population, not the fitness. Then we mutate the population, and then we say, this little bit here just basically says if we've got a new best attempt, or like a new nearest attempt. If so, we're just going to print it just so we see some sort of progression in the console, and I'll show you why this is quite nice later. Then we iterate the generation count just so we know how many generations of this algorithm we've done. So yeah, that's it. It's quite simple, hopefully. So yeah, just gonna add a couple of print statements, and then I'll run it and we'll see. So I'm gonna print the population, I'm gonna print the fitness, what else? I'll print the normalized fitness, whoops, normalized, and I'll print the population again after, let's copy paste this. I'll print the population after crossover, and I'll print it after mutation. Whoops. And then what I'm going to do is I'm just going to actually have this called once, and I'm also just going to have it call it for 10 population size, and I'm going to have it break right at the end here whether it finds the right answer or not, just to give an example of this first bit. So I'm going to actually cancel this right now, this brute force thing. You can see it's not working. It will eventually work, but it's going to take ages. And you can see here, whoops, you can see here, it's using a lot of RAM. So yeah, you can see this is not a very good method of finding characters. You can see as soon as I cancel that program, this RAM usage is going to go right down. There you go. How to clean up 8-9 gigs of RAM, whatever it was using. So if I call phase 2 now, that's this script right over here. We're going to do it on cats again, so it's 4 letters. This is just going to be to demonstrate each step. So hopefully you can see this. I have a feeling this is hid slightly behind. There you go, you should be able to see all that now. Okay, so initial population right here, we've got 3 characters, remember, for 4 characters. I'm going to actually make this just 3, just to make it a bit more readable. So yeah, repeat that. Okay, so 3 characters in our first element, 3 characters in our second, and you can see like we've got dollar signs in here, we've got full stops, we've got capital letters, we've got lowercase letters, we've got everything in here, right? So there's our first one. Now this is where we get our fitness score. Our fitness score is a minimum of 1. I didn't actually mention this. I probably should go back to the code and mention it. So down here, where's it at? Where do I say? Oh, right here. So if sum of fitness is equal to 0, the sum of fitness is actually equal to 1. We're going to change it to 1 because we're going to divide by the sum of it, and obviously this will give errors if we are dividing by 0. So this is just to stop errors basically, and mean that we're always taking from the old population rather than generating a new one again. So this does crossover. We're not actually going to see anything here because it's got none that are right. Let me just repeat this again until we see characters chosen that are right. This is harder than I thought. There we go. So you can see this one. That's this one right here. It's got the C for cat. This actually has a fitness score of 1, and therefore the rest are all 0 because it doesn't need the sum of fitness is not equal to 0, therefore it doesn't need to set equal to 1. So what this does now is it's only going to be picking this. So this is the fitness printed out. This is the normalized fitness. So you see on these other ones it totaled to 1. On this one it still totals to 1. And you'll see, I'm going to up this in a second, you'll see this always totals to 1. Now it's going to, for crossover, it's going to always be selecting, because this is 1, it's always going to be selecting this array for parent 1 and parent 2. Now obviously this is just a really unique case because it's such a small population, and I'm only running it like this one time, I'm not iterating through it like I should be. So it's always going to pick this as its parents. So you're going to see here for the population, it's actually just printed it out 10 times, as we would expect. But then this is why mutation is important. So you can see here again it has printed it out 10 times. But if I take out this break up here, this one right here, if I take this out and I just set this off to run, you'll see it actually found cat eventually. Wow, that's loud. So you can see in our population at CPT, so you'd expect in the next population, since it's only going to be choosing from CPT, it's going to just repeat that over and over, you'd expect. But because we've got this random mutation in, you can see down here on this line, this is the mutation line, it actually by chance just changed this P to an A, and then it knew it found cat, and therefore we broke out and stopped. Now it took 3,600 generations to find, but you see mutation actually allowed it to find it, whereas it would not normally have found it. If I change this mutation rate to 0, so you see it now has no mutation at all, it's just never going to find it, it's just going to loop like this forever. I'll just stop it now because hopefully you can see my point. So yeah, you need a mutation rate in there so that you can find stuff like that. Actually, one last thing with the 0 mutation rate. If I up this population size to 100, you'll see this is actually stuck in a loop. I'm not sure how high I'm going to have to make this, but you'll see if there's enough variation in the population, there we go. If there's enough variation in the population, we do actually find it, because you can see we've got all these different strings to choose from, all these different letters. So you can imagine that we found a C here, we found an A here, we found a T here. So if we happen to pick these two parents, which would perfectly be possible because this has a fitness score of 1, this has a fitness score of 2, both of these are going to be viable candidates. Then there's a 50-50 chance it chooses this, 50-50 for this, 50-50 for this, and therefore that could produce our answer, which it did. It might not have been those two arrays because you can see a lot of these actually end in T and C, start in C and have a middle letter A because it knows roughly what it's going for. So you can see you don't need a mutation rate, just you need a large population if you're not going to have one, and it means you have a chance of getting stuck in an infinite loop if you don't and stuff. So you definitely want a mutation rate, but whether or not you need one is up for debate. So Last couple of things I'm going to show you. I'm going to take out these print statements. Whoops. Okay, so if I save that, now if I take out this mutation rate and we have just the population size of 1,000, you'll see it found it in 0.2 seconds. Now if I add the mutation rate back in, it found it in 0.19 seconds. Now that's not significant, but you see, sorry, this population size is too big for this. Actually not, it's not. Okay, so it found it in 2 generations in both. It found it in pretty much 0.2 seconds on both. Now if I up the population size back to what it was, and I added an extra letter, but I take out the mutation rate and we run. Now you see it found cats with a 0 mutation rate in 0.2 seconds. And 0.19, so it beat it again. Now this might be significant, I'm not too sure. I'm not certain if that's enough to go on, the fact that it's beat it twice by like pretty much the same margin. But you'll see, if I keep making this bigger, there is going to be a significance in the speed between the algorithms, one with the mutation and one without. So 1.4 for the mutation and 1.5 without. So I think it's fair to say that mutation rate is actually helping with speed. Now, the reason we print out like this is because you can actually see it does gradually get to the answer. So you see, like up at the top here, it's got no letters right, and as you go down, you see it's got an A for the cat, it's got an S, it's got the N for and in the right place, it's got the S for dogs in the right place. And you see down here we actually get the word cat. So yeah, hopefully you see in there that it does gradually get towards it. Now, if I keep making this longer, you're going to see it's probably going to get stuck here, because there's now more chance that we don't have enough variation in the population. So you see now it's stuck. It's not actually improving on this. Because the population isn't varied enough, because we've only got 1,000, and because there's no mutation rate. So if I cancel this, this is again the importance of a mutation rate, and then I run again, you're going to see we will eventually get there. And there we go, so it took 6.9 seconds and we found it. Now, one last thing with this code, then I'll show you the improved one. This video's getting quite long. So you'll see here we're probably going to get stuck. This is kind of on the limit of what I've found. You can see it's kind of getting close to what it should be. We've got like up here cats and dogs, and we've got almost and we've got other, and then we've got almost things, and then almost longer, and it's really close, you can see, but it's not quite there. Like this down here is like nowhere near. So yeah, you see it's pretty much stuck now. It will improve and eventually it will get it, but it's like it's not doing it quick enough for my liking. So you can mess around with the mutation rate, you can mess around with the population, and you figure out like certain values work with certain targets. But an interesting improvement you can make in genetic algorithms is generally in how you score your population. There's how you score, how you cross over, and how you mutate. There are 3 areas that you can really tweak the algorithms and make them better. So for this particular example, I found that a really good improvement to make is down here where we calculate the fitness. Rather than just calculating the fitness and then adding the score to it as its fitness, so you'd calculate how many letters were right and you'd use that. I found if you could add powers of the score, it helped a lot. Because if you imagine, say you've got 4 letters and 2 of them are right. Now, the difference between having 2 of them right in one and 3 of them right on another, it's not really a lot, because although it's only 1 letter, there's only 2 more to find. Do you know what I mean? It's not that big a difference. I don't know how best to explain this, but basically, having an extra letter right, although it doesn't seem a lot because it's only 1 number, it's actually really significant, because there's a 1 in 100 chance of having each letter right, sort of thing. Well, 1 in 95 chance. So you need some way of saying, if it's got a higher number, pick it significantly more of the time, not just a little bit more of the time. So what you can do is down here for fitness score, you can add in a power. So we'll do like power 2 down here. I'm going to cancel this now. You can see it's pretty much stuck. Like, it is improving. It improved at generation 551, but it's still stuck. So I'm just going to cancel this and then save, and we'll run this again, and it might work now. I'm not too certain if this works, but we should see improvement hopefully. So now what it's going to do is it's going to square the fitness before it puts it in. So this just basically changes the graph from a linear graph to a quadratic graph. Hopefully you understand that. It's not too important if you don't. All you need to know is that we're changing the way we calculate the fitness. Okay, so I'm going to leave that run in a second. I'm going to move on to the next bit of code I want to show. So what this is it's the exact same thing, but this time it's got a couple extra things. So it's got power as a variable. This is just where I put that 2. I've put power instead, just so we can change it up here. What else is there? Let me just cancel this guy. I have a feeling that's going to go wrong because it's not this code, and this code was the one I specifically designed to use the power. So as far as I can remember, this is exactly the same, just including the power. I also experimented with trying, oh sorry, this is a change as well, the mutation rate. The mutation rate is actually 1 divided by the length of the target. I figured that the longer the target was, the lower you'd want the mutation rate, because if you've only got 1 letter to look for, you'll probably want to just randomly pick a character over and over until you find it. If there's 2, you'll probably want to be mutating less than that, and obviously if there's 1,000,000 characters, you won't want to be mutating 1 in every 100 characters, because then you're just going to be mutating too much. There's going to be too much variance. I found that on average you were going to be wanting to mutate like 1 character per string was quite a nice number, and this generally does that. So I tried changing the mutation rate, and I still think this is actually quite a good idea. Basically lowering the mutation rate based on like the average fitness of the population or something. I think that's quite a good idea, but I've left it out just for this experiment. You'll see why. It seems to work pretty well like this, so I wasn't too unhappy. And by this point I'd already learned all I wanted to learn, so I just wanted to move on. So I'm just going to run this a couple of times. We'll just mess around with this, and then that'll be it for this video. So what we're going to do is we're going to search for this phrase here, and we're going to search I think 10 times. Yep, 10 times. Is this still running in the background? Yeah. No, it's done. Okay, so is this ready? So you can see I've dropped the population to 100. This is going to improve performance quite a bit, and with the mutation rate, it's fine. 100's fine. I'll up it to 250 just because it'll probably help us speed, but we'll experiment with these numbers and I'll show a couple of ways that we can improve speed in a sec. Okay, so we'll give this a run. We'll see. Yes, this is working. So what was this phrase that we couldn't find? If I take this phrase, the power as well, you can see, sorry, is the length of the target. So I'm going to change this in a second. We'll mess around with that as well. I'm Make a new target just so I can keep that one. Okay, so I'm also going to make a new power. Just going to make that 2, and we're going to see if it was to do with the other algorithm being broke. Yeah, so you can see it's getting really stuck trying to find this text. The other one got stuck on this text. This one also is with just a square power. It's still making progress, you can see, but it's not really that good. If I up this power to 4 though, let's see if that works. So I'm just going to cancel this. If I up the power to 4, so you can see the text does gradually get there, like cats, and we've almost got dogs. You can see as well, it's quite interesting, some of the letters change. It knows that there should be an O here, but sometimes it'll change to like a 0, but it knows to fix it in like the next generation. I thought that was quite smart, quite interesting to look at. Like even when it slightly goes wrong, overall in the population there's enough right letters in that slot that it knows to fix it. Quite clever. So yeah, you can see this one's getting stuck as well. I've actually got closer than the last one, but it still got stuck. I've upped this power to 10, this is the last number we're going to try. Yeah, there we go, so it actually solved it for 10. So a higher power helped in this case. Taking a little while down here, but I'll keep it like that a sec. What I'm going to do now is I'm just going to go back to the cats example and just show how quick this is at finding cats compared to the other ones. I'm just going to let this one finish first. Quite interesting to see what the time is for this. Actually, one more thing I want to check. I'm going to get rid of this power and use the length of the target. So whatever the length of this is now going to be our power. It's probably like 100 or something. Maybe not that big, maybe 50, something like that. Either way, it's going to be significantly higher than 10. So we'll check the time on this. I'll run it with the new power, and we'll check the time on that. I might also mess around. This actually is a decent size string out. This might be the one that I mess around with the population and mutation rate. We'll see. Should be almost done now. I think it's probably done about 8 or 9. There we go. So it took 118 seconds, so about 2 minutes to find. Now with the new power, so we've got 2 minutes to beat. Let's see what this does. So you can already see it's significantly faster. The reason I wanted this mutation rate and the power to rely on the length of the target was because I figured for lower target lengths it probably wouldn't be as necessary to increase the power. And I figured there would have to be some relation between them. I'm not sure if this relation is the right relation. It probably shouldn't be length of it. It should probably be different, but I had a feeling it should have some relation to it, so I chose to go with this one. You see here it's done already, it only took 47 seconds, so a huge improvement from changing this power. and it wasn't a fluke. I can tell you that I've run this a couple of times and other times. So yeah, hopefully you get this. If I change this population size, we'll do this to check the speed increase we get from this, or decrease, we'll see. So you can see it's flying through generations a lot slower now because it's got more population, a higher population size. So I can't actually imagine this is going to be faster than the previous one. There's a nice balance. So on the one hand, you want a big population because you want a lot of variety and you want a lot of scores to choose from in choosing your next population. So on one hand, you want a big number here, but the bigger this number is, the slower your algorithm's going to be, and it pays to be able to loop through quickly and iterate through your generations really fast. So there's a nice balance between too many and too little. I think 1,000's too many, and I think probably 100's verging on too little. With like a 95 character range, you probably want, I'd say 200 would be quite nice. 250 worked well. I'm not sure what the perfect range would be, but it's probably in that range somewhere. So yeah, hopefully this was interesting. If anyone's interested in the code, let me know. I can post it somewhere, but I don't know if anyone will be interested in this. It's not particularly thrilling or involved. So yeah, mess around with these if you want. If you do get me give you the code, mess around with the population size, mess around with the mutation rate, change the power. You can change the length of your target. Like I tried to find the like the opening scene of Romeo and Juliet. That's what the line is right there. I'll run that in a sec. You can see what it does. It's quite interesting, but it doesn't really work. I drop this down. We'll set 200. Change our target out. Hopefully this is done in a sec. I don't think this is going to take much longer. But yeah, if anyone wants to improve on this, look at the method for scoring and the method of crossover. They're the particular areas of improvement, I think, and this power might not be the best. I have a feeling this is actually going to break because I think this number's too big for this particular one. Oh no, there we go, it's fine. So you see here it sort of keeps the letters the same. The reason it's doing that is because this power is so high. It's just basically keeping letters except for the mutations. That's why I don't think this relation is right. It should probably be like length of target. I don't know, maybe it doesn't really want to be linear, I don't think. I'm not sure. It wants to have some relation to the length of the target, but it doesn't want to go up this fast. Like this here, there's not enough crossover going on. This is all just mutation doing it, because it's basically just picking the highest fitness score and going with it, and then mutating through like individual letters, and then if one of them letters is right, it'll keep it. What this is doing here is more like a lock picking example of like doing the first tumbler, and then once that one's right, keep that one, don't move that one, we know it's right, so it'll do the next tumbler. And it's not, this is less genetic and more like more of a clever brute force sort of. But yeah, you can see it does work. We've got like the 2, we've got households almost, bar that W. Both alike in dignity, in pair. So I don't think that should be pair, I think that should be fair. Yeah, it should be, it says right there. So yeah, in fair Verona, where we, is it begin? Oh no, where we lay our scene. Don't know where this is coming from then, but you can see it's, you can read it already. It's pretty easy to make out. So it does work. It'll eventually get there. It's just, yeah, I don't think this is particularly genetic anymore. This is more just clever brute force. So yeah, this has been a really long video, but I figured I'd put this out there because I thought it was quite interesting. Anyone interested in coding is probably going to find this at least vaguely interesting. I liked messing around with the mutation rate and the target stuff, and there's quite a lot of potential with these algorithms. The next one I did was significantly better than this and a lot more interesting. So yeah, I'll be posting a video on that sometime in the next few days. So yeah, thanks for watching. If you enjoyed this, leave a like. If you want to see more of this sort of content, or the next video when it is released in a few days, hit the subscribe button. And for now, thanks for watching.